This is a note recording for 7th hour, Monday, 10:23 for math analysis. And we just were looking at some problems where we were looking at continuity. And now we're going to look at the intermediate value theorem. If you need a little more time after I talk about this, you can sure turn or pause the recording and look at everything. But otherwise, this is the intermediate value theorem. And I think we use this mostly for kind of that bottom part in this particular class. So I will read it. If f of x is a continuous function and a is less than b, and that is a and b are going to be on the x-axis, x values, and there is a value n such that n is between f of a and f of b. So then there is a number c such that a is less than c, which is less than b, and f of c equals n. And so really what that is saying is if you have an a value and a b value on the x-axis, and c is someplace in between, that wherever f of a is, so that y value for f of a, and f of b, that the y value, f of c, is between those two y values that we had at the beginning. So that's kind of this intermediate value theorem. There's an intermediate value in between. And then we use this corollary a lot. This is the location principle. If f of x is continuous function and f of a and f of b have opposite signs, and so f of a in this case, in this visual picture, is negative and f of b is positive. So they're really illustrating this corollary with our diagram. And if they have opposite signs, which they do, then we know that there's some value c in between where f of c is equal to 0. And so really then the c value that they're picking is right there for this location principle. If we pick that value right there, then f of that value is going to be equal to 0. So essentially there is a 0 between a and b. And that should make sense to you, because what we're saying then is if one of our y values is negative and our next y value is positive, in between those two x's, there is a 0 as we go. And so if you need more time to write the intermediate value theorem, you can pause this. Otherwise, I'm just going to go on and we'll use this to approximate our zeros. Keeping in mind right now you get to use a graphing calculator, so that can be helpful, but try not to use it kind of as too much of a crutch as you're going through things. So this is 3a, and it is determined between which consecutive integers real zeros of f of x equals x squared minus x minus 3/4 are located on the interval between -2 and 2. So this is an interval between -2 and 2, including -2 and 2. So we might make a table of values, and that table of values would have x values -2, -1, 0, 1, and 2. And we just want to know between what consecutive integers there are zeros. So that is good enough for us to find. Since I'm not here, I'll just show you those. Take a minute, write down that table. And then the big thing you should be noticing here is that between this y value and that y value, we go from a positive to a negative. So that means between -1 and 0, there is a 0 or a root, and then it stays negative from there to there, but then from between the x values of 1 and 2. The y value is negative and then positive again. So there's another 0 in between those two. So we can say that there are 2 zeros in the interval, and I'll just kind of show this answer. There are 2 zeros on the interval from -1, which is less than x, which is less than 0, and the interval from 1, which is less than x, which is less than 2. If you want to validate that with a graph, you can see that if you graph this function, the zeros do fall between those integers. Here's -1, 0, 1, and 2, between -1 and 0, and between 1 and 2. So you can use your graph to kind of help you check that. Try to use the table of values to kind of compare those positive and negative values as you go, so that you can kind of really get that idea of what's happening. Because eventually in a math class, you may not be able to use or have access to that graphing calculator. For instance, if you take pre-calculus at SMSU here. And let me just kind of cover those a minute. My bad that I'm showing you those a little too early. And so for 3b, our problem is f of x equals x to the third plus 2x plus 5. We want to know about zeros in the interval from -2 to 2 again. So again, you're going to make that table of values and kind of just see where the y values are changing sign. And just a reminder, you could actually take this function rule and just put in the values of like -2, -1, 0, 1, and 2 to see. Or at this moment, you can also use your calculator. I'll just show you those again. And then you should be noticing that between when x is -2, f of x is -7. When x is -1, f of x is +2. So in our interval that we were given from -2 to +2 for x values, that sign change is coming between -2 and -1. So we know that there should be a 0 between -2 is less than x, which is less than -1. And again, we'll look at that graph now, and you can see that here is the value for -2, here's the value for -1, and it crosses that x-axis, or yep, it crosses that x-axis between those two values as you look at that. So that should be pretty straightforward. We can narrow that down further by going by halves or by tenths and just get a little bit better view of what's happening there. Now, the next thing we want to talk about is end behavior. I'm going to go ahead a couple slides here. And the end behavior tells how that function just acts as you go to either end of the graph. So when you're looking at x going to -infinity to the left, or when you're looking at x going to +infinity to the right. We've already looked at what happens at a particular value, and we've found those limits. Now we're looking at our end behavior as we go. And generally, end behavior is going to increase without bound, decrease without bound, so go to either positive or negative infinity, or sometimes it'll go to a value like maybe 0 or some other value if there's a transformation there. So write down some notes about this. End behavior describes how a function behaves at either end of the graph. That's what happens as x increases or decreases without bound, becoming either greater positive or more negative. And so our left end behavior is going to be described like this. So when you're giving that, it's the limit of f of x as x goes to negative infinity. And then our right end behavior is the limit of f of x as x goes to positive infinity. And that's like a fill in the blank, is equal to blank is equal to blank. So when you're giving the end behavior, those are kind of the general setups that we're looking at. And this graph that's shown here, maybe you want to just sketch that a little bit, but as our x values go to negative infinity, so we're going more and more negative and walking along that x-axis, I'm looking up and that graph is getting further and further away. Ooh. And so as x goes to negative infinity, then y, or f of x, is going to positive infinity in this case. And so I'm just going to slide that over a little bit. So we would say the limit of f of x as x goes to negative infinity is equal to, in this case, positive infinity. So that's that side of the axis. And then if we look at the other side and what happens as x goes to positive infinity, I'm walking along here and I start to see them negative numbers, and I can tell that they're going more and more negative as I get further and further away from 0. And so as x goes to positive infinity, that f of x values, you can see, are going to negative infinity. And so then when we write this one, we'll say the limit of f of x as x goes to positive infinity, in this case, is negative infinity. So that's what's happening there. Now, we're going to look at some function values. And again, at this point, we're looking at a table of values and kind of seeing what happens as we go to those extremes, either negative infinity for x or positive infinity. So here's our next problem. It's f of x equals x to the third minus x squared minus 4x, plus 4. And we want to describe its end behavior. So I right now know that my answer is going to be the limit of f of x as x goes to negative infinity is blank, and then I have to fill in the blank, and the limit of f of x as x goes to positive infinity equals blank, and I have to fill in the blank. So it does say support your conjecture numerically, and so when we do that, we want to look at a table of values. Now, when we look at our table of values, we might have 0 in there, but now, just like we had not used an exact table, we're going to use super big positive values and super big negative values. So take a minute and make this table. When x is negative 10,000, when x is negative 1,000, when x is negative 100, when x is 0, when x is 100, when x is 1,000, and when x is 10,000. Your calculator might give you those e values. Write those in scientific notation. So if you get like negative 1 E9, that is negative 1 times 10 to the 9th. You don't have to write all those zeros out as you go. You might want to pause this because I'm going to show the answers now, give everybody a chance to make that table. So pause this and then I'll go back. Okay, you should have had enough time to answer these problems. And so here's what you should have gotten. At negative 10,000, it's negative 1 times 10 to the 9th. At negative 1,000, it's negative 1 times 10 to the 9th. At negative 100, it's negative 1 times 10 to the 6th. At 0, it's 4. At 100, it's 1 times 10 to the 6th. 1,000, 1 times 10 to the 9th. And at 10,000, it's actually positive 1. There's a little error on the slide there. Positive 1 times 10 to the 12th. And so now we can use this numerical support to say, okay, as x goes to negative infinity, x is going to negative infinity, well, y is also going to negative infinity, or f of x goes to negative infinity. And then as x goes to positive infinity, it appears as though x, or f of x, which is y, goes to positive infinity as well. So when we write our answer, we're going to say the limit of f of x as x goes to negative infinity is equal to negative infinity, and the limit of f of x as x goes to positive infinity is positive infinity. And then if you want to check that graphically, you can see that if you're walking along the x-axis and headed to negative infinity, that graph is headed down to negative infinity as well. And if you're walking along that graph to positive infinity, the graph is shooting up and going to positive infinity as well. So there's our answer. And use that graph maybe just to kind of check to see how things are looking as you go. Now, the next problem that you're going to look at is this number 5, example 5. And here, the graph is going to approach a specific value. And so we want to have an experience where things might look a little bit different. So this example, this number 5, our rule is f of x equals x plus 2 over x squared minus x minus 2. Just a little note to self, and I'm not going to leave it there, but if you do type this in, when you do type this into y equals, make sure that you have parentheses over around the numerator and around the denominator as you go, so that you can see what's happening. And we had those ones where we approximated things last Wednesday, so make sure that you're sure you know where things are going. And if the values that I put on this table aren't enough for you, then make sure you kind of look at those to see what's happening. The table of values I'm going to ask you to do is from negative 10,000, negative 1,000, negative 100, 0, 100, 1,000, and 10,000. So I'm trying to give you kind of similar tables every time so that for the different kinds of problems you know what to choose. Again, pause this if you want to take a moment so that everybody can figure that out, and then I will show those in just a minute. So here are the values that you should have gotten on your table. Negative 1 times 10 to the negative 4, or 0.0001. And then negative 0.001, negative 0.01, negative 1, 0.01, 0.001, and then 0.0001. So there's your values. So as x is going to negative infinity, think about what's happening to y. And now I'm just going to rewrite that as 0.0001. These are getting to be super small numbers. This is, if I only went to the nearest tenth here, these would all be zeros. So it looks as though this f of x goes to 0 as x goes to negative infinity. Oh, I'm going to write that a little better, negative infinity. And then as x goes to positive infinity, it appears as though they are also going very, very small, and f of x goes to 0 as well. So by our table of information, we would say that the limit of f of x as x goes to negative infinity is equal to 0. And we would say that the limit of f of x as x goes to positive infinity is also 0. If you want to check that graph, when we look at that, here it is. And the book authors didn't do a super great graph here because I am just going to point out that it looks like that goes below the axis, but it should be just above the axis. Oh, but getting closer and closer. So I can't fix that on the slide at this point. So if I'm walking along this x-axis, and oops, I meant to draw that in green. If I'm walking along this x-axis and I'm going to negative infinity, my y values are getting closer and closer to 0. And so that's how I get this limit. When I walk along my x-axis to positive infinity, my y values are still getting closer and closer to 0. So those are our two end behaviors. End behaviors, what's happening out at the end of the graph. And then we just have a little application problem to look at. This is our real world example number 6. So the symmetric energy function is E equals x squared plus y squared over 2 if the y value is held constant. So the y value is going to be held constant in this one. So we can kind of just think of that as a numerical value. In a minute, I'll just put a number in there. What happens to the value of the symmetric energy when the x value approaches negative infinity? So I'm just going to write first the equation, that this is E equals x squared plus y squared over 2. And just think about that y being held constant. So, you know, if it's constant, it's a single value. So if it's 1, 1 squared is 1. If it's 100, 100 squared is going to be 10,000. But either way, when that's held constant, we're just adding some numerical value, and it's what x is happening, or excuse me, it's what's happening with x that's going to affect that. So I can make that any constant, and I'm going to choose to make it 1. So 1 squared is 1. So long term, as x goes to negative infinity, those values of x, and I'm maybe going to slide this up a little bit. The values of x, when these get to be super negative values, but I'm squaring them, they'll become positive and very big. So when I have a negative value and I square it, this is going to get to be positive, and so plus 1 divided by 2. So if I have this super big number that is positive, and I add 1 and divide it by 2, well, if it's super big, even though I'm dividing by 2, it's still going to be super big. So in this case, the limit of f of x as x goes to negative infinity is going to equal positive infinity. And you can validate that with a table of values if you'd like. That might help you kind of go through that problem. Now, with the rest of the class period that is left, you can work on page 30 to 33, which is not due until Wednesday. The reason it's not due till Wednesday is because I'm recording this and everything. If there's any questions on Tuesday, I just want to allow for that, and then we'll move on. Please be quiet and respectful, and use your time to work, and then at 3:08 you can stack the desks. Or excuse me, stack the chairs. Have a great day. See you tomorrow.